Well, good morning, ladies and gentlemen. Here we are moving on to our next section here. But before we get and introduce the section, let's back up the train here for a minute and let's do these chain rule derivatives. And what I want you to do is I want you to hit pause quick, and I really want you to see, oh, do I remember how to do my chain rule derivatives? Because if you don't remember your chain rule derivatives, and this is saying find the derivative, it's not a function defined as an integral. It's just saying, hey, y equals 3 ln x squared minus 7. What is the derivative of that function? And if you forgot how to do these, okay, really hit pause, seriously hit pause, go back, look at section 3.6. And I do recall saying back in section 3.6, hey guys, you need to take your time to memorize these derivatives now, how to use the chain rule, and if you don't, your life is not going to be good closer to the spring when we begin to integrate or anti-differentiate, okay? So take a second, hit pause, do these, see if you can remember these chain rule derivatives, because if you can't do the chain rule derivative, yeah, you're going to have a ridiculous hard time doing integration with the chain rule, and that's a special process called integration by substitution. Makes it easier. Okay, so find your derivatives. That's what you should get for the first one, because remember, I have a constant, so I have my 3 times the derivative of my natural log. And remember, the derivative of the natural log is the derivative of the business, so the derivative of x squared minus 7 is 2x over the business, and then I just kind of put it all together to simplify my equation. How about number 2? Number two is an exponential equation. Oh, what's the derivative of e to the x? It is e to the x, so y prime equals, it's e to the something, so it's e to the something times the derivative of the something. Well, it's derivative of cosine? Yeah, that's right, it's negative sine x. And then you got to really be careful. You want to give that little bugger a hug, so when you reorganize this, you say negative sine x times e to the cosine x, so you don't think your negative sign ends up being a subtraction sign, okay? And then when we came along here to number 3, if you remember, yeah, I highly encourage you to rewrite these as exponents. All your roots were fractional exponents, and what I'm really doing is I'm taking the derivative of something to the 1/2. So the derivative of something to the 1/2 is 1/2 that something, drop my power 1 to the negative 1/2, times the derivative of my something, and then I simplify that little bugger to get basically the square root of 5x squared minus 7, and that would be a 5x in the top, right? Well, why are we going back to do these chain rule derivatives? Well, the reason we are going back to do our chain rule derivatives is because if we know this is the derivative, it is our responsibility to know the integral of 6x over x squared minus 7 dx. It's going to be our responsibility to know that that is going to be 3 ln, and now we know the absolute value of that business plus our constant c, okay? And it's harder to see. We can see our derivative of our natural log. Our powers here are differing by 1 power, and I can see right here, if I took the derivative of that bottom, the derivative of the x lies in top, and I'm not really worried as much about that 6 because I can fix that 6 with a constant, right? Well, how about here? I'm thinking I need to know what's the antiderivative of negative sine x times e to the cosine x, and well, because we know the the derivative of e to the something is, it's going to be e to the something, okay? And, well, where the heck did that negative sign come from? Oh, that came from the derivative of the cosine. So this little bugger right here, when I'm anti-differentiating, it's getting absorbed back into the inner portion of the function. And because it's an indefinite integral with no limits, I need my plus c on it, okay? And they're, these are all starting easy. I really need to look at what's the the integral of 5x over the square root of 5x squared plus, I think it's 7. Minus 7, sorry. I'll change that out. 5x minus 7 and 5x squared minus 7. So when I'm doing it, they get a little bit harder and a little bit harder. So what we did is we typically would rewrite something like this the same way we do with our writing our derivatives. We like to see them as negative exponents. And that way I can see them like, oh, okay. I'm really seeing here, if I took the derivative of that, I'm going to get an x. I'm going to get actually a 10x, and I'm not as concerned about the 5 because I can fix that 5 with a constant by multiplying by something. So I'm like, oh, okay, this is going to come back. So I'm going to take my 5x squared minus 7. I got to add 1 to that power, and then I'm like, oh, but I really need a 5 in there, right? And then how do I get that 5 in there? And things really start to get complicated. And then you're like, okay, what we're going to do here, let me get this thing off. What we're going to do here is we're really going to kind of focus on this little bugger. And we're saying this is going to be what y equals. So let me work it backwards. And then I'm going to have 1/2 5x squared minus 7 to the negative 1/2. And then that's going to be times by a 10x. And I'm like, oh, okay, that's where that little bugger's coming from. So I got that half, and that 2 is going to cancel out the 10. So what, where's that coming out? Where's that going to? Where's my antiderivative going to be? And I'm like, oh, okay, so that half is taking care of all of that business that I have there, right? And I'm like, oh, okay. So when I come back through here, I see that is taking care of it, and I didn't even have to fix it because when I'm power ruling that down, that took care of it. Well, it's going to get complicated, okay? Well, what do these look like? We're reversing the chain rule. In reversing the chain rule, there is a, whoa, I don't want that. Reversing the chain rule has this, can be done by a process of integration called substitution. And it really makes things easy. Do I always have to use substitution? Absolutely not. Okay? So as you're coming along, if you're identifying, ooh, look at that power in the derivative of the bottom, I can see the derivative of 3 plus x cubed. I know the derivative of that's going to be 3x squared. Bottom line, I'm focusing. I see my x squared. I'm not concerned about the 3. I can fix that 3. Okay, so I can work things backwards and say, oh, okay, so this is a natural log, absolute value, 3 plus x squared. I wouldn't need the absolute value on this one because any x I put in there is going to be positive. And then I got to kind of, oh, that's not squared, that's cubed, sorry. And then I got to kind of think about this. Well, my chain rule is going to give me the 3x squared, and I only want an x squared out. Oh, I need that 1/3 plus my c to get me there, okay? And then as we're moving along to our next one here. And you're like, really? Yeah, this one's not too bad because I can see the derivative of tangent is secant squared. So my antiderivative of the secant squared x times e to the tangent x, well, that's going to be e to the tangent x plus c, and we are always checking that e to the tangent x times the derivative of the tangent is the secant squared x. We are always coming along And yep, okay, we matched what we had, so we got it with our plus c. Well, the further and further we go, the more and more complicated things are going to get, okay? Because as I'm moving along, I'm like, yeah, well, you know, coming up with this little rogue number that I can multiply to fix my coefficients, it's going to get harder and harder and harder to get, okay? And what are you talking about? Well, I'm kind of looking at this. Again, I can look inside here, okay? And I know inside there is going to have a derivative of a negative 3x squared. And bottom line, I'm looking on the outside with my product. I can see my x squareds there. So I'm really concerned about my variables on the outside. And I'm not as concerned about that 5 because I can fix that 5 with numbers, okay? And this one's really hard for me to demonstrate this way because my brain does not work this way. I use substitution all the time on things like this. But this is going to make us look like, okay, this is a 5x. No, it doesn't equal that. Come on. It's going to be a 5x squared, and then it's times 7 minus x to the third to the 1/3 dx. So then we're going to kind of start to work along through here, and we're going to push our way through this. And we're like, okay, if I anti-differentiate it, I know I got to power rule this thing up because I know here is my inside function. And remember, the chain rule came from a composition function of f of g of x. So there's my inner function. And I know when I anti-differentiate that, that's going to be a 7 minus x cubed. I'm going to add 1 to my power. That's going to give me a 4/3. And I'm like, whoa, I need a 5 out there. And I'm like at my plus c, because I can see my x squared going out. I'm like, whoa, this is really getting kind of weird. How am I going to get a 5x? You know, where is that coefficient coming from or going to? So then I'm like, okay, let's look at this. Let's work it backwards then. So if I started taking the derivative of this, okay, I'm going to be at 4/3 times 7 minus x cubed raised to the 1/3, and then I got to chain rule that times a negative 3x squared, and then the c would be gone. So I can see right now my derivative, if I simplified this, I'm going to have a negative 4, 7 minus x to the third to the 1/3, and I should put my x, let me throw my x squared over there. Okay. So I really got my negative 4x squared, and see all the important pieces, my x squared and my function to the third, there's my x squared and there's my function to the third match. However, that 5 doesn't match, okay? So I need to fix this thing somehow. Somehow I got to multiply this by some constant to fix it, because I need that to be a 5 out there. Well, how am I going to get that to be a 5? Well, I guess I don't need the 4, right? So I'm kind of looking back here. I don't really want that 4, so I'm going to multiply by a 4th to get rid of that 4, okay? But I do need a 5, but not a negative 5, a positive 5. So I guess, what am I going to do here to get there? Well, I guess I got to multiply by a negative 5 to get that 5. So looks like now, if I have that, because, you know, we're looking for what do we multiply out in front here to get that 5. And hopefully you're seeing how complicated this is getting. But let's check this out. My 3 is going to cancel there. My 4 is going to cancel there. And then that's going to give me my negative 5 for my derivative, right? And what that's going to do, let me get right here now. So if I added that 5/4 in there, that's really going to give me my negative 5x squared. Oh, not negative, because that 5 is going to cancel out too. And it's going to be a 5x squared, 7 minus x cubed to the 1/3. Aha! There we go. There's my plus c. So I'm looking at, whoa, what did I just multiply by? Well, I had to add a 1/4, right? I multiplied that times 4 and times a -5. So I ended up taking this times -5/4. That was the magical mystery number that I needed to make this out, -5/4. Because now if I take the derivative of that function there is my antiderivative, which is sitting underneath that radical. And hopefully you're like, yeah, that is getting complicated. I don't want to do all those that way. And some of you guys are really good at that. You're really good at guessing and checking. But it's kind of tough, you know, when I'm thinking about all this. And what we really do, okay, if I look back and say, okay, I don't want to go there. Let's say I had the integral of like x to the 1/3 power. Yeah, I can do that. I think just about anybody can do that. That would be x to the 4/3, and we're like, hey, I need a 3/4 out there to fix it, plus a c, okay? And anybody can do that, and that's what substitution allows us to do. It allows us to take something very complicated and rewrite it very easy to make that antiderivative come out very easy. What are you talking about? Well, here's what I'm talking about. And if you, oh crap. And if you watch this anywhere else in the world, you will not see my quite the same technique that I use. This is something I kind of developed on my own, because coming up with this thing when I was in college and stuff, and the professors were coming up with that number, I just could not wrap my mind around it very well. And I really struggled for a while, so I came up with my own process in my U substitution. And what we are going to do is, you know, that this is why composition functions are very important, because you have to be able to identify what is the inner function, meaning, oh, son of a biscuit, meaning what I really want to do is I need to be able to say, hey, the outside, the outer piece, that is coming from that derivative in there. Therefore, that is my inside function. And what we want to do is we want to rewrite this entire integral, okay, so that it's really easy. What our goal is to get this thing down to something like this so we can rewrite it. And using substitution allows us to do that. And it's kind of cumbersome at first, but please follow, trust the process, and it doesn't come overnight. It comes with practice, as everything does in here. But we're going to look at our inside function, and they call it U substitution. So you can call it whatever you want, but I always let U equal my inside function, okay? And we're going to actually use a derivative to rewrite this. So what I've just done is I've kind of looked at this like, hey, 5x squared, and then now I have the cubed root of u, and this is, like I said, this is my own system. And what I have written right here is not mathematically legal because I'm not in multivariable calculus. I have a single integral, and all of these always have to be in variable harmony. They have to be in the same letter at all times. But I just learned the process. I'm going to show them what they want to see, and then I'm going to get rid of what they don't want to see. So that's what I'm showing you. And then what we're going to do is we're going to actually use a derivative to replace it, because we need everything underneath this integrand. We need everything in here to be in terms of u. So what I need to do is I need to make sure everything with my x goes away. Well, the only way to get rid of a dx is to replace dx with substitution. Well, if I look here at my u, how I defined u, if I take the derivative of that with respect to x, this is going to give me du dx, and that's going to equal, well, what is the derivative of 7 minus x to the third? That's going to give me negative 3x squared, right? Well, what I did then is I take both sides times dx, and I would say, oh, du equals negative 3x squared dx. Okay? Because now what I would do is I would solve my equation for dx, and I'd say, hey, that's going to equal du over negative 3x squared. And I'm going to take this statement and this statement. These are the two I use. And I'm going to take this back here, and I'm going to come right back here, and where I see my dx, okay, I'm going to replace my dx with what I just solved it to be, which is du over negative 3x squared, okay? And notice this is all over 1. So then what I'm going to do is, oh, check that out. The things I can't have in there, they just reduce out. So I really am looking at 5 over negative 3 square root of u du. And it's not a square root of u, it's a cubed root. I'm sorry, I wrote that wrong from the beginning. And then I'm going to use a property of an integral. What do you mean a property of an integral? And you're probably saying, whoa, Kruger, we had a negative 5 over 4, not a 5 over 3. Trust me with this, there's a property of an integral that allows us to pull constants outside. And then I'm going to say this is u to the 1/3 power du. And like I said, everybody can find the antiderivative of that, right? So now what I'm going to do is now I'm going to say, oh, I have negative 5 over 3 times, this is going to be u to the 4/3, 3/4. Oh, you see the negative 5/4 now, don't you? And then that's going to be a plus c, and I'm going to multiply these numbers I see, those go away, and I get negative 5 over 4 u to the 4/3 plus c. However, they wanted my antiderivative in terms of x, right? So then I'm just going to come right back to how I defined my u right here, and I'm going to substitute that back into my function over here, because u, negative 5 over 4, u here to the 4/3 power, is actually 7 minus x cubed. And I can get it without nearly as much thought. I just trust the process, okay? So I'm going to do a couple more here. How can I use substitution to help these integrals? Well, I'm hoping you don't need it on one like this, but if you do, because I'm looking at this and like, oh, okay, here's my inside function, and I know the derivative of sine, that's coming out of a chain rule. So this is actually going to equal e to the sine x plus some constant c. But if you don't see that, okay, think of your chain rule. Think of e to the u. What is the derivative of that with respect to x? It's e to the u times u prime, right? There's my chain rule. So it's e to the something. So think of it. My something, u, is going to equal my sine x. So now I am rewriting this integral here as the integral of cosine x e to the u, and there's my dx. Now remember, I said I got to get rid of that, and I got to get rid of that. So I need to take my derivative, and I don't have to show this work, but usually you're going to go du dx equals, derivative of sine is cosine, sorry. I got to take the derivative of that, so this is going to be a cosine x, and then I'm going to multiply this side, and usually from here when I do this, I know my dx is going to have to be on the left, and so I would usually go right to there, and I would bypass that, okay? And then I would say, excuse me, dx equals du over cosine x. So all I'm doing is I'm substituting things in. So now I'm going to come back here, and where my dx is, and you're going to mentally see it right away and go through it, you're going to replace your dx that I just erased with a du over a cosine x. And then you see this whole fraction is over 1. I can see that cosine x goes away. So I'm really looking at the integral of e to the u du. Well, what is the antiderivative of e to the u? It's e to the u plus c. Oh, wait a minute. Everything was in terms of x, so now I just go back and I resubstitute in for my u to get my antiderivative. Okay? How do I know what to substitute for u? U is my inner function. U is always my inner function. I can see this as a natural log, okay? So if you don't see it, use the u substitution. And how do I know? Because if I took the derivative of that, the derivative of that is going to be here. And what I'm focused on is I'm focused on the variable. So now that I see the derivative differing by a constant on the top, okay, see, I just put that 2. You're going to see this 2 come out. I'm going to let my u equal the bottom. Therefore, what I've just done is I've rewritten this integral like this, and my 6x squared is going to be up there, and I have my dx. But I'm going to erase that dx, okay? I usually wouldn't even write that out. And I'm going to say du equals 3x squared dx, and I get rid of writing the left side as a differential, and then I say dx equals my du over 3x squared. Okay, so I'm really going to come back here and I'm going to substitute. Whoa, that almost is bad news. And I'm going to substitute in for my dx. I have a du. Oh, look at this. This one was already a fraction. X squared. Notice my variables. Isn't that kind of nice? My variables reduce out. And this is going to turn into, well, it's really 2 over u du, isn't it? Well, that 2 is a constant. And you know the antiderivative of 1 over u du, you know that's the ln absolute value of u. So here is the template that we're really looking for. So I'm going to pull that 2 out, as I would usually do it, du. And I'm going to say, oh, that's 2 ln absolute value of u plus my constant. Then I'm going to come back, and I need to make sure I get rid of u in terms of x, and there's where I had it defined. So that's a 1 plus x cubed. So there is my antiderivative. And if you see it way back here, I know many of you do, if you see it back here, my powers are the same. Okay, this is going to be a natural log 1 plus x cubed. And if I took the derivative of this, this is going to give me 3x squared over 1 plus x cubed. You're like, oh, I need a 6. Oh, I better give it a 2. And then I get there. That's fine if you see it that way. Okay? But you're going to run into problems where you're not going to see them that way. Yeah, they're going to get a little bit harder. Here's another one. Composition function. Inside function. You see how if you take 8 plus 4x cubed, you take the derivative of that, you're actually going to get 12x squared, but again, I'm focused on the variable on the outside, okay? So I'm going to let u equal 8 plus 4x cubed. I am hence going to take the derivative of this, and du is going to equal 12x squared dx. So then, this is my own little system over here, du over 12x squared. I am going to substitute in basically, let me show you. Crap. What I'm going to actually substitute is I'm substituting in for this and I'm substituting in for that, so I can rewrite everything in terms of u. Okay, so I say, hey, you're going to equal the integral of. I'm going to take this. I'm going to say that is the square root of u. And then I'm going to leave that x squared there, and I'm going to leave this dx is coming out. Okay, that dx is going to come out. That's a du over 12x squared. And then I'm going to reduce, and I can see, okay, those cancel. So I really have 1/12 u, because I want to see my powers now, u to the 1/2 du. Now, I'm never going to leave this, I'm never going to leave this guy there. Come on, baby. So I'm never going to leave that there, but I am going to, so I'm going to erase it, and that 12th, I'm pretty much always going to go right out front right away. And then I know I can take my antiderivative as 1/12 times u to the 3/2, which is a 2/3, plus c, my constant, which means then I'm going to say, hey, you're a 1, you're a 6. That's going to be 1/18 u to the 3/2 plus c. And then I got to make sure I resubstitute this guy back in, and I get 1/18 times 8 plus 4x cubed to the 3/2 power plus c. There is my antiderivative. Okay? One more. Just do this. I think this is going to be the last one I'm going to do today. And then we're just going to have no homework tonight. We're going to finish this up tomorrow. We're just about long enough here. Trig functions. My inner function. Hey, if you see this right away, meaning, oh, I get it. What's the? This is the derivative is sine. This is sine something. So the sine came from where? Derivative of cosine is negative sine. So this is going to have to be negative sine of my something. And then my chain rule here, that's going to give me my derivative. That really gives me a 2x over here. But I need an 8x. Oh, I need a 4 in there plus c. That's my antiderivative. If you're like, what in the crap did he just do? Okay, don't worry about it. Substitution is going to allow you to organize. Inner function. U equals inner function. We're going to take the derivative of the inner function. We're going to solve that derivative for dx, du over 2x. I'm hence going to take my integral, and I'm going to rewrite 8x, and I'm going to call that a sine of u. And then rather than put my dx in there, I'm going to put du over 2x, du over 2x. Then I can see my x's reduce out. My 2 is going to go to a 4. So this whole integral is really 4 times sine of u du. And you know what the antiderivative of sine is. I know you do. It's my constant times, what's the antiderivative of sine? That would be negative cosine u plus my c. And then I'm going to say, hey, what was u? Oh, this is really negative 4 cosine x squared plus c. Okay? If you want to work ahead a little bit, guys, I really don't care. You can keep trucking through this note sheet if you want to start some homework. But I'll tell you what, when you get up to, oh, I don't know, number 10, number 11, and number 12, those are going to be a little bit tougher, and they're going to get a lot tougher than that. So you need to work hard at these. Have a good afternoon, and I'll have part 2 tomorrow. Thanks for playing math.